All right, number 6. We're told that a chemist adds 50 liters of 0.002 molar zinc 2 plus ion to 25 liters of 0.15 molar ammonia. There's a reaction that can take place. It's involving the formation of a complex ion, here where the zinc is coordinated to the ammonia. That has a humongous equilibrium constant. The Kf is 7.8 times 10 to the 8th. That equilibrium lies really far to the right. In other words, ammonia reacts with the zinc to a very large extent to bind it up to form this complex ion. And that's pretty typical of many ligands when they bind with transition metals. Okay, so that's the type of chemistry we're dealing with. Now, what are we asked? We want to know what is the equilibrium concentration of the zinc 2 plus if all of this is true. Okay, so let's take a look at this problem, dive right in, and see what sense we can make of it. When I'm working the complex ion equilibria problems, I really like to treat them first, to a first approximation, as a one-way reaction, a one-way street. Okay, so I build an initial inventory in terms of RICF, in terms of the number of moles of all my components. Okay, do it in terms of number of moles. I wrote that a little bit big. I'm going to try to write it a little smaller so we can have space. And if I write it in terms of number of moles, and if I assume that it goes to completion as a first approximation, this problem becomes much more like what's called a limiting reagent problem. And you'll actually work those back in General Chemistry 1. So my first step would be to figure out how many moles of everything I've got. So I'll start with, let's say, the zinc 2 plus. So the chemist used 0.002 mole per liter solution of the zinc 2 plus, and he or she used 50 liters of it. Okay, so if I multiply 50 times 0.002, I got 0.1 mole, a tenth of a mole. So that's how much zinc 2 plus ion is present. Now, in a similar way, I could do a very similar calculation for how much ammonia was added to this system. I think it's going to be a little bit more based on the first glance at the numbers here, but let's double check, okay? So 0.15 mole per liter ammonia, that's my molarity. Whenever I take molarity and multiply it times volume in liters, I can get moles. Now, he or she only used 25 liters of this stuff. It's still quite a bit, but the concentration was higher. So if I multiply 25 times 0.15, I finally get 3.75 mole of ammonia. So I actually have quite a bit more ammonia. That may play a big role here. 3.75 moles, what I put in my eye. Now, before the reaction takes off, I'm not going to have any of my complex ion, am I? But now we assume that because the Kf is such a big number, that the reaction goes far to the right. And my first approximation, what I'll call my first draft of reality, I'm going to assume that this is a limiting reagent problem. And all of the chemicals used up that can be used up, the reaction proceeds completely to the right. Now, that's not true because it's an equilibrium, and we have to keep that in mind, and we'll have to do that later, right? But for now, in my first draft, I can assume that's the case. So if I do that, I'm thinking here that I'm going to use up all my zinc. And because it's a 4 to 1 molar ratio in the stoichiometry, I'm going to be able to use up 4 times as much of my ammonia. Now that sounds like a big deal, but because I had so much more ammonia to begin with, look, I'm still going to have a lot left. So indeed, my limiting reagent in my first approximation is my zinc. I run out of that first. I've got plenty of ammonia left. Now in this process, I'm also going to prepare or generate zero point 0.1 mole of my complex ion. I start off with none, but since it's a 1-to-1 stoichiometry between the zinc and the complex ion, I generate an equimolar quantity. So what I just did is I assume that the reaction went to the right to completion. And I make that assumption because my Kf is so big. But the thing is that Kf is not infinity, is it? It's not. So this first draft, this 0, this 3.35, and 0.1, it's got to be wrong. It might approximate reality, but it's not a perfect approximation. The reason why is because if I plug those numbers back into my equilibrium constant expression, those numbers are not going to yield that value for Kf, are they? So I got to fix this. Where I'm at right now might be a first draft, a rough approximation of reality, but it's not completely truthful of reality, is it? But now that I know sort of where I'm at, chemically speaking, I can actually come back and revise my first draft. I can make edits. To help me do that, I'm going to rewrite the equation, zinc 2 plus, combining with 4NH3, setting up an equilibrium to make the complex ion, zinc NH3 sub 4, and the whole thing is still 2 plus because ammonia is neutral. Okay, so I start with that, and I'm actually going to build a Rice table here. So I'm switching back to E instead of F, where the E stands for, of course, the true equilibrium amounts. So when we fill in our ice tables, we've learned already that we have to start by defining our initial conditions in terms of molarities, capital M. Now up top, up here, I did moles, but now I'm switching back to molarity units. So before I can go any further, I need to figure out the molarity of all my substances involved. And I use my first draft to help me do that. My first draft predicted that I didn't have any moles of my zinc. So I'm going to start with that. I'm going to say I have none, 0. However, my first draft predicted that I had 3.35 moles of the ammonia left over. Just couldn't use it up. So I could compute the ammonia molarity by taking that 3.35 moles that was left over, dividing by the total volume. Now I'm looking back to the original problem, and it seems to me that 75 liters is our total volume after these materials are mixed. So I'm going to have 3.35 moles, and I'm going to have that dissolved in 75 liters. If I do the math, my molarity is equal to 0.0446, repeating, 4467. That's my molarity of ammonia. So I can go back to my rest table and write that value in, 0.0446. Makes sense, right? Now I do the same type of thing for the concentration of my other substance. Now what is my other substance that I've got some of? Well, I've got this complex ion, the zinc, where it's bound up with the ammonia, right? The whole thing's 2 plus. Okay. Still 75 liters total volume. But now, how many moles of that stuff do I have? Well, I've got far less. I've only got 0.1 mole in my rough draft up top, don't I? So what I need to do is take the 0.1, divide that by 75 to find the molarity. And my molarity of this material, expected at the start of my experiment here, or the establishment of my equilibrium, is 0.00133 repeating mole per liter. So as you probably guessed, I'm going to write that number right here. All right. So far so good. We've written our reaction, and we've written in the initial concentrations in terms of moles per liter for all of the substances present. Those molarities, of course, resulted from our first draft. Now we knew our first draft was not representative of reality because the values that we came up with here, here, and here cannot be plugged back into the equilibrium constant expression and get that number. We'll get something very, very different if we did that. In fact, we'd have a bit of a problem because this zero would cause all sorts of mathematical problems for us, right? So we have to alter that first draft, and that's what our Rice table is doing for us, right? Don't lose sight of that. So what's wrong with our initial first draft projections? Well, I think this zero right here is our big problem. This is an equilibrium. It's a constant that is not infinity. So this reaction really doesn't go to completion to the right, to the highest extent possible. The truth is, the reaction lies somewhere in between, right? It's a true equilibrium, a two-way street. So while the zinc is really good at binding the ammonia, it's not perfect. So because of that, having this zero right here overestimates zinc's ability to bind. What we should realize is that while we're going to have a small concentration of zinc, it's not going to be zero. And if I shift the rough draft equilibrium back to the left, I'm going to make some of that zinc 2 plus ion. I don't know how much I'm going to make right now, but I'm going to make X molar of it. And likewise, if I'm going to shift back to the left, I'm going to make some more ammonia. I'll have unbound ammonia. How much will I make? Well, I'm not exactly sure, but if I make X of zinc, I need to make 4X of the ammonia. So what will I have at equilibrium? Well, 0.0446 plus 4X. That's how much I'll have in terms of its molarity. And then last but not least, our complex ion. Now our complex ion, we had too much of it to start with, right? We over-predicted the ability to bind to form that stuff. So we're going to use some of it. So it's going to be a change of minus something. Now, minus what, right? Well, we're going to make minus X molar because of the 1 stoichiometry out in front, right? So we'll have 0.00133 mole per liter minus X as our expected equilibrium concentration of that. So all we've done is we've come up with a Rice table, and from the stoichiometry of the reaction, we've now figured out what we should expect at equilibrium. And you probably guessed right at this point. What we're going to do next is we're going to solve for X. To do that, we need to go to our equilibrium constant expression, Kf. Now we know the value of Kf in this problem. We're given that up above. 7.8 times 10 to the 8th is our Kf value. And as with any equilibrium constant, the Ka is always equal to products raised to their stoichiometric coefficients divided by the reactants. So in this case, up top, we have our complex ion equilibrium concentration, don't we? And down the bottom, I would need to plug in my concentration of zinc at equilibrium and my concentration of ammonia at equilibrium. That latter one needs to be raised to the 4th power by virtue of this 4 right here. So all we need to do is figure out what concentrations of these substances satisfy this mathematical equation, and we're done. We know our first approximation should get us pretty close, but not exactly there, because again, in the first approximation, that would be a 0, which would cause us all sorts of problems, right? Mathematically. So we got to fix that. Our Rice table is allowing us to start to do that. Now, we don't know what the molarity of this complex ion is, but I know from my Rice table that it should be represented by 0.00133 minus x. If I could figure out what x was, I'd know what that value was, right? Similarly, I don't know what the concentration of zinc is right now, but I'm going to find it here in a few minutes. But I know that the molarity of zinc can be represented by my variable x in the mathematics. And likewise, I don't really know what the concentration of ammonia is at equilibrium, but my Rice table allowed me to project that the ammonia concentration should be equal to 0.0446 plus 4x. Is that all making sense? So just, I think at this point, make sure that you understand where I got all these numbers from. I think maybe you're following along, right? We use our Rice table to figure out what the equilibrium concentrations were in terms of x, and we've only just plugged them into the Kf expression. And like I said, we've been doing that for weeks now, right? All right, now our next goal is to solve for x. So we start to shift to the mathematical portion of this project, or this problem. What I'm saying is, in the numerator, there's a number that's added or subtracted to or from x. And that's prime for a chance to make a simplifying assumption, isn't it? We just have to kind of decide if we think x is going to be real small or not. Now x, if we go back to our equation above, it's essentially representing the change that occurs as the system reaches equilibrium. And we know that the Kf value is a humongous number. So indeed, this equilibrium really does lie far to the right. And this initial approximation, this first draft that we built, should be pretty close to being correct. So what that tells me is x is very likely to be very small, and I probably can ignore it right here. Similarly, I can also probably ignore that x down in the denominator. Because even if I multiply it by 4, it's probably going to be really, really tiny compared to 0.0446 molar. Now doing this really simplifies my life a lot, doesn't it? Because I got rid of that variable in the numerator and the denominator. Oops, and the net effect of all this is that numerator reduces down to 0.00133, and then all I need to do in the denominator is raise that concentration to the 4th power. So let me do that on my calculator real fast. So 0.0446 times 0.0446 times 0.0446 times 0.0446. So when I do that, on my calculator, I got 3.957 times 10 to the minus 1, 2, 3, 4, 5, 6. I multiply that by the x, and that's got to equal my Kf, doesn't it? So to clean this all up then a little bit, and I'm going to have to make myself a little bit more space here. I'm running out of space. I think I'm going to erase this one and start working above mathematically. So to clear that denominator, my next step is going to be to multiply both sides by that term. if I do that, I'm functionally going to have kf, which is a number, right, times 3.957 times 10 to the minus 6 times x, and that's going to equal to 0.00133. So I just cleared the denominator. I'm going to have to erase this down here. So all we're now left to do is to solve this equation for x. And it looks like to do that, we need to take the number that's on the right, 0.00133. We need to divide that by kf multiplied times 3.957 times 10 to the minus 6. Erase that, that's kind of misleading. Okay. All right. So that's what we need to do mathematically. So let me look at this denominator here and maybe clean that up a little bit. So I'm going to take that 3.957 times 10 to the minus 6, and I'm going to multiply that by my kf. My kf is, of course, 7.8 times 10 to the 8th. Excuse me. So when you do that math, in the denominator, I can do that product, multiply it out, get 3086.27. And then all I need to do is 0.00133 divided by 3086.27. And when I do that, I'm going to have to create some more space here, so I'm going to use my space wisely. I got 4.31 times 10 to the minus 7 mole per liter. 4.31 times 10 to the minus 7. And that's equal to my x. Now, if I look back to my rice table, what exactly does this value of x tell me? Well, for one, it tells me my equilibrium concentration of zinc, doesn't it? And in the problem, if I look back, that's what I was asked for. So as a consequence, this x value that we solved for is basically the answer to the problem. But if I wanted to, I could figure out what the concentration of all these other substances are. I know now what the concentration of the free and unbound zinc is. But I could also find the concentration of ammonia, couldn't I? With my excess plus the 4x. And indeed, my assumption was valid. Look how small this number is. 10 to the minus 7 compared to 0.0446. Remember, that was just from the excess from our first approximation. I could also easily solve the final equilibrium concentration of my complex ion if I want to. I just take what I expected to have in my rough draft, the 0.00133 molar, and subtract x. So because I solved for the equilibrium quantity of the zinc ion, or I solved for x, if you want to think about it that way, I can really figure out how much I have of all three substances at equilibrium. So this problem was a little bit different. I mean, there's a lot of common ideas embedded into what we've done, right? But it was a little bit different. And what's really different about this with the KF business is I like to come in and do a rough draft first. And to help me do that, I assume that the reaction's a one-way street, that it proceeds to completion, and then after that, we move back to the left. And that was done down here, right, in the rice table. The reason why I prefer to do this problem this way, rather than in one swoop and just jump right into the rice, is because we like to make simplifying assumptions when we can. especially in this case, because the stoichiometric coefficients tend to not be 1, okay, in many cases. And that makes the math a lot more complicated, right? You got a 4x term down here. You got to raise that concentration to the 4th power. So if we could make a simplifying assumption, it actually really helps us out a lot. And by doing this rough draft business and assuming it goes to the right to completion first, what that does for us is in the second step in this Rice table, it assures that x is going to be really, really small. And that allows us to make this simplifying assumption in more cases than not. All right, so I hope you enjoyed this problem. Complex ion equilibrium is kind of fun. It's an interesting concept. A lot of really interesting chemistry goes on in the aqueous phase that sometimes we just kind of gloss over and don't think much about.